All right, good evening, everyone. I'm broadcasting today a day early because of this. My juror summons. I'm going to be down at downtown at the, what is it? New York Supreme Court, and I'm not sure what time I will be done, so I'm broadcasting early. Anyways, I'm going to get started now. The lecture will take about the usual amount of time, maybe 50 or 60 minutes today. Summons, I'm going to be down at downtown at the, what is it? There we go. A little bit of technical difficulties. Anyways, the lecture will go for about 50 minutes, and then at the end of that, I will do some review of the exam. And if anyone is online live by then they can ask questions. Otherwise, I'll just sort of go over it a bit. Okay, so I'm going to start the screen share now. And I do have the Q&A going, so if you are tuning in, please feel free to send me a note to let me know you're there. So today's topic is sampling variability in the central limit theorem, and it's going to be the basis for everything else that we do this semester. So I'm going to start with an overview of population versus sample, something we've talked about before and is straightforward. Depending on how you look at it, it's straightforward in theory, but it actually still can be a common source of confusion once we start talking about sampling distributions. So it's something that I want to cover very carefully and make sure you're clear on. Then I'm going to introduce to you the central limit theorem and a little bit about how you can use it, and talk about experimental and observational studies, prospective and retrospective, as well as some common study designs. And these are covered in your textbook, open intro, a couple sections in chapter 1 on study types, and in chapter 4 on sampling and the central limit theorem. So once again, the population versus sample, which I've mentioned before. The population is everyone who we're interested in a study, but typically we are not able to observe an entire population unless it is a census, and so we observe samples, and samples are chosen to be representative of the population, but they're an incomplete amount of information, and so we will have to make inference based on a limited sample of the population. And you'll recall that we represent these differently in our notation, using Greek letters such as mu to represent things to do with the population, and we use regular alphabet letters such as X for things relating to the samples. So a little bit of vocabulary about sampling, and we will start out with with a bit about sampling and types of sampling that we do. So study units or sampling units are the individual elements of interest. So in the example we see here, those would be people, but it is possible for them to be things other than they might be a geographical region or a school if we were to be measuring only things about those entities as a whole. The target population is the ideal population that we are interested in. So it could be everyone in the US, it could be everyone in New York or Massachusetts, but it's some well-defined population that is the object of our study. And then the study population is the population from which we actually sample, which ideally would be the same as the target population, because if it is different, then that systematic difference is called selection bias. And a classic example of that is surveys that meant to target all Americans of voting age, but for example, used telephones at a time when not everyone had a telephone, so that the study population was adults with a telephone, and the target population was all adult citizens. And then finally, the sampling frame is just a formally written down list of all the units in the study population that we can use for sampling. So in order to draw a sample, you need to start with some large list that you can then use a random number generator in order to produce samples. Just a reminder, we use Greek letters for population parameters such as mean, mu, and standard deviation sigma, and our English alphabet for sample statistics such as X and S. There are a number of ways we can sample. The ideal way, and the way that a lot of the tests that we describe in this course are going to be based on a simple random sample, and this is the easiest type of sample to analyze. And all this is we have our target population, our list of records, and we simply choose from them at random. And we would normally use a random number generator in order to do this. And in R, there's a function called sample. In any programming language, there are random number generators that we could use. So under this strategy, every individual in our study population has an equal probability of being selected. Now, systematic sampling would be where, so we have 30 individuals here, we would select one random number instead of 10 random numbers, and then we would systematically select the rest. So if we chose our first random number randomly and it was 2, then we would just go by 3s, 5, 8, etc. And then we would treat this as a simple random sample. Stratified sampling is an important refinement of the simple random sample. And this is where, when you have attributes of your target population that you wish to draw in a pre-specified proportion, either in the same proportion as in the population, or potentially you want to increase the prevalence of some of these populations in your sample, you divide your sampling frame into these strata. In this example, we have blue sort of blobby people, black square people, and red people with mini skirts, and we want to draw from them in a guaranteed proportion. So we would, after they're divided into these strata, we would sample separately from each of these. So we have the 10 blue people here. We would, for example, choose 3 of them at random, and then 3 of the black square people at random, and then 3 of the miniskirt people at random. And that way, it's still a random sample, but we know what the prevalence of each of these strata will be. And the advantage of this can be that it actually reduces the variability of things that we estimate from the sample, and ensures that that every sample will be more representative of our target population. Cluster sampling is something that we won't get into this class, but it's an important strategy in public health studies where there is some natural groupings of the units, and it would be very difficult to sample at an individual level. So, and a classic example of this is if we wanted to study an intervention that was done on schools, for example, changing removing soda machines to see how much of an impact that had on this soda consumption of students. That is something that you couldn't really implement at the level of individual students. You would have to implement at the level of schools. So if you had 100 schools, you might randomly select 10 schools for the intervention, another 10 schools for your control for comparison, and then you would individually sample students from each of those schools. That's a cluster randomized trial. So then finally, those are all probability samples where the researcher defines the probability of selection and knows what the probability of being selected is for each individual in the sampling frame. Non-probability samples are where we don't know what the probability of selection is, and it's not controlled by the researcher. So, for example, you put an article on, or you put a notice on the internet or in the newspaper calling for volunteers, and then your subjects are whoever comes in to volunteer. Or patients at a cancer clinic, that's whoever happens to come into that clinic. And these are often called convenient samples because the researcher is not under control of who the participants are or what their probability of selection is. And these are prone to selection bias. But they're still not uncommon because there are situations where there is no other way to do it. Here's an example just to help make it a little bit more visual, maybe, of the different sampling strategies in a geographic setting. So here's a map of an area. So this is, say, an area with some sites of archaeological interest that are buried. We don't know where they are, so we're going to go and do test plots in various areas. So these are the hidden things in yellow here, and that we want to find. So how are we going to do it? Well, we would start, if we're going to use a systematic approach, by turning the entire site into grids that we are going to search. A simple random sampling approach would be to simply then, we would number all of those grids. That would be our sampling frame, and then just choose from them at random. And it would look something like this, second picture here, the simple random sampling. Then a systematic sample would look something like this third one, where where the position, we would divide it, say, into, we have what, about let's say 35 larger grids here. Then we would choose the position in the grid at random, but then use that same position in every subsequent grid. The stratified random sample would be one where, okay, we're splitting this region into two. There's the part to the north of the river here, and then the part to the south of the river. And then choosing our sampling sites to guarantee that we have equal representation of both of those zones in our sample. And that might be advantageous if we had some, where there's a clear delineation of regions and we want to be sure that every region gets represented equally in our random sample. Finally, non-probability sampling, there's nothing random about it. It's just where we would go and choose some plots based on what we thought was interesting, for example, or maybe what was convenient, easy to get to. So here's the example in the textbook on population versus sample. This is the Run 10 data set. This is 16,924 participants in a 10-mile run, and we have all of their running times. So is this a sample or population? If our target population were all of the participants in runs everywhere, then perhaps this would be a sample. It depends on who you're interested in. If we're going to do inferences about smaller subsets of this, and what we're interested in is the 16,924 runners, then this would be our population. And then subsets of this, say 100 runners picked out, would be a sample of this population. And here's an example of that. We've got a histogram on the left of all 16,924 runners and a sample on the right of just 100 of them. And you can see that these histograms look about the same, except that the counts, the frequencies, are of course smaller when we only have 100 of them. But the center is about the same at a little less than 100, and the spread, between 40 and 150 is about the same. I'm just going to take a quick look here, see if anyone has joined in yet. Oh yes, we have one viewer. Welcome. Please don't hesitate to write in a question if you have any. So what you saw on the left there was a population and then a sample. So what is a sampling distribution? A sampling distribution is the distribution statistic of the sample for many samples. The most common one that we're interested in, especially in this course, but in general, the most common statistic that we're interested in for a sample is the mean. So if we're thinking about the mean, the way we would generate a sampling distribution, take a sample of 100, calculate the statistic on that sample, such as the mean, and then repeat over and over and over. And then all of those means, the distribution of means, would be our distribution. The key point here on the sampling distribution is that when you use that sample of 100 and calculate the mean, that is just one realization from your sampling distribution. So even though it's 100 sample on your sampling distribution, because you're interested in there such a time. And that sampling distribution automatically from the population distribution. There's an example where the population distribution of serum cholesterol levels is really broad. It has a mean at 211. A sampling distribution has that same mean, but see, I'm going to formalize those in a bit with the central limit theorem, but those are the central limit theorem. The mean is the same as the population, the deviation, and that it is normally distributed. That the spread of the sampling distribution, because it's the average property of a group, the average property less variable then property of individual. The sampling distribution of the means of samples of 100. Oh dear, the sound and video keep cutting in and out. Can you see me now? I wonder if I'm going to try something a little bit differently. Is this better? Thank you for letting me know. I'm not sure what the problem. Okay, well that's a bit. I'm sorry about that. I hope that you didn't miss too much of it for lack of video. Okay. Okay, so great. Thank you for letting me know, Laura. So those, I just covered some of the basics of the idea behind the central limit theorem, and maybe I'll back up a bit since we were missing video here. This picture kind of visually summarizes the central limit theorem. The central limit theorem relates a sampling distribution to a population distribution, where a population distribution is something like the ages of runners, the serum cholesterol of individuals. the key thing is that it is some property of individuals. And then the sampling distribution is the property of groups of those individuals of a certain size. So if we were to take samples of size 25, that would be one sampling distribution. Samples of size 50 would be a different sampling distribution. But the key components of that sampling distribution are that its mean is the same, its variance is less, and it is normally distributed. So the central limit theorem comes in three parts. The first is that the population mean, mu, and the sampling distribution, x bar, are identical. So this is probably not too surprising if your average runner's age in the entire 16,000 runners is 40, then as you take a bunch of samples of them of any size, then the mean of the mean ages in those samples will also be 40. In any individual sample, it might be a little more or less than 40, but if you take a lot of those samples, then the average of all of them will be 40 if you have a large enough number of samples. So the first part is that the population mean and the sampling mean are identical. The second part relates the standard deviation of the population to the standard deviation of the sampling distribution, which we also refer to as the standard error. You're going to get lots of exposure to the standard error in the next little while. And these are related by this equation that the standard error is equal to the population standard deviation divided by the square root of n, where n is the sample size. So remember that sigma, that is the variability of individuals in the population, and then the standard error is the variability of means, of sample means. And that is for, if you have samples of size 1, it will be the same, but for any samples larger than 1, then the variability of those samples will be less than of individuals in the population. So finally, part 3, and this is really a useful property, that for large enough samples, the shape of the sampling distribution becomes normal. So the distribution of means becomes normal, which is really quite incredible, that no matter what the distribution of ages or serum cholesterol levels is in the population, that still the distribution of means will be normal. So on the left, here's an example of a uniform distribution, let's say of ages. If you take samples of size 4, then the distribution of the means of those samples starts looking more normal. And the larger the sample size, up to 7 and 10, the narrower that distribution of sample means looks, and the more normal it looks. And this kind of makes sense, right? So here we have on top with n equals 1, we have, let's say these are values between 0 and 10. If you take 4 of them, you're not very likely to get all 4 of them being 0 or all 4 being 10. So those tails get less probable and the middle becomes more probable. And the larger that sample size, the more the mean is going to be bunched up towards the center. And here's a real example on the right from that Run 10 data set, where we've got all 16,924 runners. And then I actually, I calculated this, took means of varying sizes. So the first one is sampling single individuals, so n equals 1, and that distribution looks exactly the same as the population. And then we have n equals 10, 25, 100, and 1,000. And you just see it, this skew that we have starts getting less. By the time we're at n equals 10, it looks fairly symmetrical. At n equals 25, it looks quite symmetrical, and it just keeps getting narrower and narrower. So just to be very clear what I did here, this was a simple calculation. For, let's say, for this n equals 10, what I did was draw 10 runners at random from the 16,000, calculated their average age, and then plotted it. So I just repeated, I took samples of size n equals 10, calculated the average, I repeated that about 1,000 times, and then I plotted those, that distribution here, and then did that again for groups of 25, calculating the average age and doing that over and over. So for a random sample of size n from a population having mean mu, this is just a summary of the central limit theorem here. This is all three of the of those parts of the theorem summarized on one slide. That for a random sample of size n from a population with mean mu and standard deviation sigma, then this sampling distribution of the sampling mean has the following distribution. It is also a normal distribution, so we're talking about a normally distributed population. The mean is the same. The standard error, which is the standard deviation of the sampling distribution, is sigma square root of n. And for a normally distributed population, it will look like this for, or for not very large n. For an extremely non-normal population distribution, it will only look like this for larger n. So the standard error, it's something that tells us how much variability to expect in a sample statistic just by chance. It's not something that we're ever actually going to observe in a study directly. We can observe the standard deviation of individuals because we'll observe multiple individuals, but typically we'll only have one. We'll typically only have one sample, but the standard error will be something that is based on a hypothesis or an actual population that tells us for a sample of a certain size how much variability to expect by chance. And just to really hammer this home yet again, that sampling variability decreases with larger sample sizes. And this is a fundamental of experimental design, that in order to have more ability to tell whether an individual sample is a part of a pre-specified sampling distribution, there's more ability to tell that for larger sample sizes because that random sampling variability decreases with larger sample sizes. So for large samples, the sampling distribution will be normal. What is a large sample? Well, as a rule of thumb, we can say that then when the sample size n is at least about 30, that's a large sample, and the sampling distribution will be normal. That's not a hard and fast rule, in that if the population distribution is normal or close to normal, then the sampling distribution will be close to normal, even for quite a bit smaller n than that. But no matter what your population distribution is, even if it's bimodal, extremely skewed, the sampling distribution will look normal if n will still look normal if n is greater than 30. So for proportions, this sampling distribution is also normal as long as n is large. So greater than or approximately equal to 30, and with neither of the groups being too small, like less than 5. The only difference here is that we have a different, the mean proportion is again the same as the population. So if we're talking about the prevalence of smoking, if it's 20% in the population, then the mean of the sampling distribution will also be 20%, or a proportion of 0.2. But the standard error on the proportions for repeated samples is given by this equation at the bottom, the square root of that proportion times 1 minus the proportion over the sample size. And then other than that, we can use the central limit theorem in the same way. We can use the central limit theorem for inference, and we will be using it. I'm going to introduce this today, but we'll be using it for several of the tests that we do. The so-called z-test is for a single sample, a single large sample from a population of either a known or a hypothesized mean and standard deviation. So this equation, z equals x bar minus mu over the standard error, this is a z statistic for a given sample. So the central limit theorem tells us that the sampling distribution for a sample from a population of mean mu and standard deviation sigma is centered at mu and has a standard error sigma over square root of n. Then if we draw a sample of that size and observe a mean of x bar, we can calculate a z-score for that one sample. And then from the central limit theorem, assume that if the mean really is mu, then the sampling distribution is normally distributed with mean 0 and standard deviation 1. And we can calculate the probability of drawing a sample of this particular value of z or more extreme than that based on the central limit theorem. And this is the so-called z-test. We can also use it to construct confidence intervals based again on this quantity x bar minus mu over the standard error being z distributed. So in order to construct a confidence interval, we would use this property, remember from the empirical rule, that for a standard normal distribution, 95% of the probability is between minus 1.96 and 1.96. And I'm going to get into more about the mechanics of actually doing that in the next class. But you can see from this equation here that if you plug in minus 1.96 and 1.996 here and center your distribution at 0, then your confidence interval will be when some numerator over the standard error equals 1.96 and 1.96. So 1.96 times the standard error would give you your 95% confidence interval. And I don't want to get into that in too much detail today. We'll have plenty of time to talk about it next week. Summarizing the central limit theorem, this forms the basis for much of the upcoming work in this course, the t-test, analysis of variance, and confidence intervals. And what is so important about it is that it for large enough n, it tells us what the sampling distribution is, and so it allows us to do inference and draw confidence intervals on around a population mean, even if we don't know that population distribution. And what large enough n means depends on how normal the population distribution is. For a normal population distribution, it can be actually a small n, but for an extremely skewed or bimodal population, then n should be at least 30. And when you have a large enough n, then it does not matter what your population distribution is. So this last note is actually very interesting here, in that the size of the sample matters, but the size of the population does not matter. It does not enter into this calculation. The sampling distribution is determined only by the sample size n. So whether your population is of size 60,000 or 6 million, you would have the same amount of precision on estimating the population mean for a given sample size n. Just think about that for a bit. I want to highlight this, that if you have a representative sample, you can estimate the population mean just as well with a given sample size, whether your population is 600,000 or 6 million, as long as you have a representative sample. I'm going to end off here just with summarizing the two main types of data, or types of studies that we get data from in public health: experimental and observational studies. And the key distinction between these is, in experimental studies, there is an intervention that is assigned by the experimenter. And the main type of intervention that we talk about in public health is the randomized controlled trial, the RCT. And in an RCT, we ordinarily randomly assign people using one of the sampling approaches that we saw to a treatment or a control group. And this is the only way that you can prove causality, because you randomly assign individuals to your two studies, you know that there is nothing else affecting their assignment. You have the only source of control over whether people are assigned to treatments or control groups. Whereas in an observational study, there is no intervention. As the name implies, you're only observing. There are several types of these. The cross-sectional observational study is a random sample of a population at a given snapshot in time. And there's some very important studies of this type, such as the New York City Health and Nutrition Examination Study, the Behavioral Risk Factor Surveillance Study, and the National Health and Nutrition Examination Study. So in these, there are, in any given, in the year of the study, a random sample of the population is chosen, and the individuals chosen are followed up with questionnaires, with health studies, etc. The retrospective study is one where students are recruited based on health study, based on their health, status. So if you are, for example, interested in risk factors for heart disease, you select people who have already had heart disease or who are healthy, and then you look back into their past retrospectively to try to explain why some of them have gotten heart disease and why some of them have not. The prospective study is one where you randomly select your cohort at some initial time t equals 0, and then follow them through time. And there are some studies, like the Nurses' Health Study, that have gone on for decades after the initial sample was made. The cohort may decrease over time, but the important thing is that you have a period of regular follow-up on them, and then as they fall victims to disease or whatever you are interested in, you already have the past data to help explain why that happened. But regardless of the type of design, these observational studies cannot prove causality, because you can observe correlation between outcomes and risk factors, but there is no way, because you did not randomly assign those risk factors, you cannot prove that they're the cause of the outcomes of interest. Here's an example of the difference between experimental and observational studies. If you're interested in the question, does smoking cause lung cancer? Some experimental approaches might be, well, I guess your ideal study from the experimental point of view would be to randomly assign never smokers to smoking and non-smoking groups, then follow them for years to see who develops more lung cancer. That one is never going to happen. That would not be ethical to assign people to a group where you have them do something that you suspect is bad for their health. That would not be an ethical study. It's not going to happen. The other type of interventional study that could happen would be one where you start with smokers and randomly assign them to no intervention or to a cessation program, which decreases the rate of smoking, and then follow those two groups for years to see who develops more lung cancer. So this type of study would be long and expensive, but it could be done, because your intervention is not expected to be harmful to the study participation. So it's something that could pass the institutional review board and be done. If we were going to address this question using an observational study, the cross-sectional approach would be to take a sample of the population, ask whether they've ever been diagnosed with lung cancer and how much they have smoked over their lifetime. The retrospective approach would be to go and choose 50 cases with lung cancer and 50 controls without lung cancer and see which group smokes more. And then finally, the prospective approach would be to observe groups of smokers and non-smokers for several years to see which develops lung cancer more frequently, which of course would take a fair amount of time and a fairly large study, because even among smokers, lung cancer is not a terribly high prevalence disease. And through a combination of these studies, if they are all pointing towards the same thing, you might start to develop convincing evidence of a causal link between smoking and lung cancer, but none of these studies individually could actually prove this causal link. Finally, wrapping up, we've covered quite a bit today. What is a sampling distribution and how does it relate to the population distribution? And the key thing is that the population distribution is properties of individuals, and the sampling distribution is properties of groups. So the relationship between those two distributions is given by the central limit theorem. These classes of studies, experimental and observational, and retrospective, prospective, and cross-sectional studies, the concepts of the central limit theorem span across all of these classes of studies. So that's all I have for lecture. I'm going to put up end of lecture. I promised that I would do some exam review. I'm just going to see here if we still have anyone online. One viewer still. So Laura, I assume this is still you here, and you're the only viewer. So I'll ask you first if you have any questions about the exam, and I'm going to start pulling it up. Let's see, where is our exam? Oops. I need to adjust something about this exam. Okay. I'm glad you found the exam straightforward. If you don't have any questions about the exam, I might actually postpone the review until I have time to announce it with a bit more time and we get some people attending who did have questions about the exam. So thank you for attending, Laura. I'm glad that at least someone was able to. And everyone else, sorry that I won't be in class tomorrow. If I do get out early, I will come in anyways, and we can use the time period to watch the exam or watch the lecture together, or to go over the exam and do other things if I get out of my jury duty on time to do that. All right. So good night, everyone, and I'm going to save the exam review until I have some more people online, or if I can come in person tomorrow. All right, good night.